What great shoes. Hi, folks. I'm here today to talk to you about the central limit theorem. It's chapter 8 out of this here textbook, Basic Statistics for Business and Economics, by the authors Lynn Marshall and Wathan. If you don't have this textbook, that's okay. You might still learn something today. I just wanted to give props where props are due as far as these PowerPoint slides are concerned. I did modify them a bit for the purpose of this lesson, for the purpose of my class. I have taken out the sections on sampling procedures. It's great information, but for the purpose of my class, it's not really where the focus is. The focus in chapter 8 is this wonderful, beautiful thing called the central limit theorem. The things we want to take away from chapter 8, from talking about the central limit here, is really getting to the standard error of the mean. The standard error is a super, super powerful tool that takes advantage of two of the most important things in statistics. First of all, it takes into account variance, which is really what makes measurement important and cool. And second, it incorporates sample size. We all know intuitively that a larger sample is better. And while we may not be able to articulate exactly why that is right now, the standard error combines those two things that are super important, variance and sample size, to become a very powerful and useful tool in estimating population means. The other things we're going to talk about in this chapter are sampling error, or the difference between a population parameter and its sample statistic. And then we're going to get into some of the details of the central limit theorem. We're going to introduce a distribution called the sampling distribution of sample means. We're going to talk a bit about how the shape of a population is affected by the central limit theorem. And then we're going to talk about how the size of samples consequently leverages the power of the central limit theorem. We're also going to take a little deviation, haha, fun, into looking exactly what the z-score is for means. Spoiler alert, it's the sampling error divided by the standard error, two things that we just introduced right here. The first question is, why do we even sample the population? Now, there's lots and lots of reasons, but here's 5 really great ones. First of all, to contact an entire population would be super time consuming. Populations are huge. We rarely have access to the entire population. Even if we did, it would take an awful lot of time and a huge amount of resource. Second, I'm talking about huge amount of resource, the cost of studying all the items in a population would certainly be prohibitive. We don't have the money or the time to do so. The physical impossibility, the third point, how would we even know if we reached everyone? We wouldn't even know. Maybe they're everybody, who knows? But that who knows part, well, we're just talking about it being really impossible. Even if we did know, could we even do it? Fourth, the destructive nature of some tests. Let's say, for example, you were studying car safety, maybe car safety of something like a Mercedes or even a Bentley. How many crash tests would you want to do with a fancy, fancy car? Not many. So we likely want to try to get as much information out of as few broken cars as we can. Now, the last part's pretty cool. It's that because the central limit theorem, because statistics themselves are so powerful, we don't even need to study the entire population to be very confident and to know exactly what's happening in the population. Long story short, we don't have to reach the whole population because we can do it with statistics. So the first term mentioned in the introduction is this notion of sampling error. Sampling error is the difference between a sample statistic, such as x bar, s, s squared, or p, and its corresponding population parameter, mu, sigma, sigma squared, or pi. In all of these cases, we're suggesting that you might be able to calculate sampling error. But in order to calculate true sampling error, we would need both our sample statistic, easy to come by, and the population parameter, almost impossible to come by. Rarely, if ever, do we know true sampling error because rarely, if ever, do we actually have access to the entire population and thus the population parameters. Still, the notion of sampling error is really useful for a lot of the things that we're going to do. And theoretically, they do allow us to make some more sense of some different types of problems we might encounter. As far as really exploring the central limit theorem empirically, I think Salman Khan does a fantastic job in his Khan Academy videos, specifically the ones on, he's got one on the central limit theorem, and specifically, if you go to YouTube and search for sampling distribution of the sample mean, you'll find one under his account, Khan Academy. I think he does tremendous work, especially his use of the demo for the onlinestatbook.com tool. It looks like what you see on the screen right here, where you have a parent population and then you draw a series of samples to execute, creating some sampling distributions of sample means down at the bottom. He takes you through a number of different examples, and I think they're great explanations. I don't want to try to do any more than he did there, so your first thing you got to do is go somewhere else. I'm all right with saying that. But as far as the explanations that I can give you in a short period of time here, the idea of the central limit theorem is that if you start with any different type of population up top here, you can have a bimodal, you can have a severely skewed, you can have a uniform, it can be skewed in another direction. You can start with any population, and then you take from it, that population is way up here, it's the parent population, it's what exists in the truth and the sky, and it's the real thing, so I keep it up there. What I can do is take a sample of whatever sample size I choose. Let's say I sample two things from that population. And then I want to take the average of those two things. And then I want to repeat that over and over again. What do I do with these averages? Well, I'm going to go ahead and plot each average I take, each mean I take, of a specific sample size. And when I plot those means on a distribution, you can see the second row would be the result of taking all possible combinations of sample size 2. And this is how the shapes of these distributions change. So as opposed to having something that looks exactly like the parent population, whenever you take the mean of these two things and plot them, you can get a distribution that looks slightly different. Let's say, as opposed to taking sample sizes of 2, you said, give me 6 of those things, and you plot it on a distribution. Give me 6 more of those things, and you plot it, and you do that again and again and again and again and again for all possible combinations of sample size 6. If you notice the shape of these distributions, they look almost nothing like their parent populations. In fact, they look pretty normal to me. In fact, if you were to say, give me 30 of those, and you plot them, give me 30 of those, plot them, give me 30 of those, plot them, and you do that for any one of these distributions, this is where you end up. All of these things are called sampling distributions of the sample mean. It's 6 words. One of them is not important, but 6 words. So sampling distribution of the sample means. Well, what we're plotting are the sample means. Because remember, I take a bunch of things, 2 or 6 or 30, and I get a mean and I plot it. So the distributions down at the bottom are distributions of sample means. We arrived at those distributions through a sampling procedure by taking 2, taking 2, taking 2, or taking 6, whatever. But that's a sampling procedure. So we call these distributions sampling distributions because we arrived at them by sampling. What are we plotting? We're plotting sample means. So they are sampling distributions of sample means. These sampling distributions of sample means, if you look at this picture, you can see clearly have something in common. The things they have in common, we can extrapolate from the central limit theorem. Now, the central limit theorem says if all possible samples of a particular size are selected from any population, just like we did on the previous slide, then the sampling distribution of the sample mean is approximately a normal distribution, and that this approximation improves with larger samples. If we take this apart, just go back to the previous slide there, we can see we start with any population, and as I said, we took all possible samples of the specified sample size, whether it be 2, whether it be 6, whether it be 30. And when we do that, any of those things down at the bottom are called sampling distributions of the sample mean. When we get a sufficiently large sample, those distributions down there approximate a normal distribution. That's what the central limit theorem says directly. There's a number of really fantastic consequences that allow us to, per 0.5 of y, do sampling statistics are often sufficient. The central limit theorem is what allows us to say that those statistics are sufficient. So these are the corollaries from the central limit theorem. For example, for any sample size, the sampling distribution of the sample mean will also be normal if the population follows a normal probability distribution. That is to say, in our previous example, we had 4 parent populations which were not normal. However, if we were to start with the population of something that is normally distributed, we'll get to an example later, something like intelligent quotient, IQ, which we know to be normally distributed in the population. When you create your sampling distributions of sample means, any sample size of 2, sample size of 3, small sample sizes, your sampling distribution down at the bottom will be normal. So if I start with something that is normal, my sampling distribution of sample means will be normal. Well, that makes sense. I'm taking a bunch of things from one distribution. I'm going to make another distribution. It should probably look like the previous one. Well, if the population is symmetrical but not normal, like one of these two here, whether it's a bimodal or a uniform distribution, if the population is symmetrical but not normal, the normal shape of the distribution emerges with a sample as small as 10. So if I take, give me 10, mean, give me 10, mean, give me 10, mean. If I start with something that is symmetrical, like this or this, with samples as small as 10, I can create sampling distributions that are approximately normal. Even these, sample size of 6, and they already start looking normal. But for a symmetrical but not normal shape, it could have other wavy things going on. It could have many, many modes or something like that. Whatever. If it's symmetrical, sample size as small as 10 will create a sampling distribution of sample means that's symmetrical. Or sorry, that's normal, approximates normal. The third, if a distribution is skewed or has thick tails, something like, let's say, income, where we know there's a lot of people who don't make a lot of money and there's a few people who make a lot of money, that would be a very strongly positively skewed distribution. If a distribution is skewed or has thick tails, it may require samples of 30 or more for this normality feature to emerge. So with something that's very skewed, we need to say, give me 30, plot it. Give me 30, plot it. Give me 30, plot it. And your plotting means, plotting means, plotting means. In order for the normal distribution of those plotted means to emerge, we need to get larger sample sizes on the order of 30. Now this is my baby right here. This is a special little moment. Um, the mean of that sampling distribution, the mean of the sampling distribution of the sample means is equal to mu, and the standard deviation of it is equal to sigma sigma squared over n. The variance is sigma squared over n. The standard deviation is sigma over the square root of n. The variance and it's all tied together. I got a little emotional there. What that last point means is that if you take, for example, let's start with the mu aspect. If you take one of these distributions and you take a bunch of samples of the same size and you plot all of those means, well, that distribution down there, the one composed of all those means, well, the mean of that distribution equals the mean of that distribution. Sometimes people will say the mean of all means equals the mean. I leave out some descriptors there. It's the mean, sure, the average, of the means. When we say of the means, we mean the mean of all the things we pull down. So we're pulling down things and we're plotting a mean. Pulling down things, plotting a mean. So we could say it's the mean of all sample means equals the grand mean, or mu. So the mean of all these things down here, that dashed line that goes up, yeah, that's the mean. It's the same mean for the parent population as it is for what's going on down at the bottom. The second part is the standard error. The variance is the variance of the sampling distributions down here is equal to the variance of this divided by the sample size that you used to make your sampling distribution. Same with the standard error. The standard error is our thing. It's the standard deviation of your parent population divided by the square root of the sample size it took to get here. We see it down at the bottom as the variance divided by the sample size, but standard deviation and standard error have more practical application than do variance. So I typically think of this as the standard error being sigma over square root of n. So these are the pictures that we talked about, but this is that thing that I got so emotional about just a minute ago. It's the standard error. The standard error of the mean is the standard deviation of that distribution we created by repeatedly taking sample means of a specific size. When we generated that sampling distribution of sample means, put that thing down here, its standard deviation, the standard deviation of all of those means, we sigma sub x bar, it's the standard deviation of all those means we took, equals the standard deviation of our parent population, the standard deviation of the individuals, that's why there's no subscript, it's the standard deviation of all those individual scores, divided by the sample size, the square root of the sample size we used to generate our sampling distributions. The mean of the distribution of sample means will be exactly equal to the population mean if we are able to select all possible samples of the same size of a given population. That again, the mean of all sample means equals the population mean. The mean of all means equals the mean. Second, there will be less dispersion in the sampling distribution of the sample mean than in the population. In other words, if your population is very dispersed, and I start to take means, and then I plot them, that plotted distribution, my sampling distribution, will be narrower, necessarily narrower, always narrower. You're never going to be able to pull two things, take the mean of those things, and find out that the mean of those two things is somehow on one side or the other of whatever your parent population was. It's never going to happen. As long as you're taking two things and averaging them, or three things and averaging them, or 100 things and averaging them, that average will always be somewhere between the lower and upper bound of your parent population. That means that the dispersion of your sampling distribution is always narrower than your parent population, which means there's less dispersion than your parent population. When we start to use the standard error, or we start to apply the central limit theorem, there's a number of different scenarios depending on the type of information that we have. In some cases, we might have sigma, we might have the standard deviation of the parent population. If a population follows the normal distribution, we know the sampling distribution will also be normal. Mentioned that previously. We also know if the shape is known to be non-normal, the sample contains at least 30 observations. The central limit theorem guarantees this thing down at the bottom will be normal. And when we start trying to apply some of the stuff that we've seen in the past, we end up with these two equations down here. Now, we've seen in the past an equation just to calculate a z-score, where we take a raw x value, subtract it from whatever our mean is, and then divide by the standard deviation. Well, if we're talking about means as opposed to individual scores, we might say, how does a sample mean differ from the population mean? Well, that sample mean has its own standard deviation. Before, when it was just a raw x score, we could say that raw x had standard deviation. Individual scores have a standard deviation associated with those individual scores. But now that we're working with sample means of a particular size, then we know that it's the mean of your sample subtracted from the mean of the population divided by the standard error. The standard error, because it takes into account the sample size, the standard error is only associated with particular sample sizes. So if your sample size changes, then your standard error changes and your z-score will change. There's two different ways we can look at this new z-score formula. This one over here is not the one I tend to use. We're going to get to a problem later and you'll see why. I tend to use this one. Either one is fine. And in fact, if you so chose to use this formula over here to calculate the z-score for an individual as opposed to a mean, well, the mean of one thing is just that thing. So x bar becomes x. Mu stays mu. Sigma represents the standard deviation of individual scores, so that doesn't change either. And then you divide by the square root of n. Well, if you take one thing, n is 1, square root of 1 is 1, you're dividing by 1. We're not affecting the result at all. You could use this formula for all your z-score needs, whether you're talking about individuals or samples, but it's a bit bulky. You don't need to do all that work. Why do I like this one? Like I said, we're going to get to it a little later. I can give you a little spoiler though. It has to deal with the fact that once I know that I'm working in the realm of means of a particular sample size, the standard deviation of individuals, the standard deviation of the population, isn't really useful to me because I'm no longer generalizing to an individual. I want to generalize to some population or make some inference about a mean of a population. So I need to be working in this mindset of we're talking about means and no longer individual scores. So the variance, the dispersion, the standard deviation I'm concerned about is not how far apart are individual scores from one another. What I'm concerned about, how far apart are means from one another? How far apart are those means? Particular means I'm interested in are the ones of the sample size I'm concerned with. In the problems, it's often stated you have a particular sample size. So I know that I'm only thinking about means of a given sample size. So as soon as I have a standard deviation for a population and I have the sample sizes that I know I'm going to be looking at, I put those two things together and that's my standard error. And that's the thing that's useful to me. So I'd rather be thinking about z-scores in terms of means and standard deviations than thinking about z-scores in terms of means, population standard deviations, and sample size. I can just say, I know I'm working in a particular sample size. Give me the standard error for that sample size, and then I don't have to worry about it again. Vocabulary time to line this all up. Another part of how all the stuff fits together so nicely is that if we say that z-score equals this guy, well, the terms that we've introduced thus far, the difference between the sample mean and the population mean, is called your sampling error. Your standard error down here is that guy. Yes, your z-score for a mean is the sampling error, how far it is from our population mean, divided by the standard error, which is the dispersion of the population, divided by the square root of the sample size. Let's get a particular example right here. Beverage. Beverage. The Quality Assurance Department for Cola Incorporated maintains records regarding the amount of cola in its jumbo bottle. The actual amount of cola in each bottle is critical. It's their product. But it varies by a small amount from one bottle to the next. It should. They can't all be exactly what they're supposed to be, but we should hope that they're generally close to that. They don't want to overfill the bottles because that means they're wasting product, but at the same time, they don't want to underfill each bottle because then people would be getting lied to. It's like those 11-inch footlongs from Subway. Its records indicate that the amount of cola follows a normal probability distribution, with the mean per bottle being 31.2 ounces. It's likely the thing they put on the label of the bottle. And that the population standard deviation is 0.4 ounces. So now we're going to follow a nice sampling procedure here, and we're going to say at 8 a.m. today, the quality tech randomly selected 16 bottles from the filling line. I don't know, closed his or her eyes, pulled a bunch of those things. Those 16 bottles had a mean of 31.38 ounces. Now our question is that an unlikely result? Given the fact that we know the mean should be 31.2, and there's probably some variance from bottle to bottle, some will be a little bit more, some will be a little less. If I get 16 bottles, and I find that the average of those 16 bottles is 31.38, how likely is it that that's within what they believe the variance should be? In other words, is the bottling process putting too much product into the bottle? Or is a sampling error of 0.18 unusual? Is the difference from our sample mean, 31.38, the sample mean we got from our 16 bottles, our experimental test of what the cola gods believe to be the real thing. It's a Coke pun. What they put on the label of the bottle. Is our sampling error different from that? Well, we go to a problem and we say, we've got this given information. They tell us that mu, our population mean, the amount that should be in the bottle, is 31.2 ounces. And they tell us that the individual bottles vary with a standard deviation of zero point 0.4 ounces. Now that's talking about any one individual bottle. Now we take a sample of 16 bottles, and from that sample we create a mean of 31.6. As I mentioned earlier, when you have a standard deviation and a sample size, and we know we're talking about sample means, I don't care how much one individual bottle varies from other individual bottles. What I care about is how much do sample means of a sample size 16 vary from one another. In order to find that, I use the standard error. So I'm going to calculate how much the means of size 16 vary from one another. So I start with sigma of 0.4 divided by the square root of the sample size, 16. That gives me a standard error of 0.1. As soon as I know the standard error, and this is a standard error specific to sample size 16, as soon as I know the standard error, I don't care about how much an individual bottle varies from anything else. I don't even care about the sample size at this point. I've got my standard error, and now I can more or less follow the procedures that I've done for individual bottles, more or less. But let's continue. We find the z-score based on x bar 31.38, mu 31.2, and sigma of the x bar, aka standard error. I love you, standard error. We do that and we calculate z of 1.8. We know that z-scores are standard scores, and we know that we can use z-scores here because of the central limit theorem. We know that means drawn from the population will be the sampling distribution will be approximately normal. We also know that for any sample size, if our parent population is normal, which this problem said it is, that our sampling distribution will be normal as well. Regardless, we know we can use the z distribution because of the central limit theorem. That's where we're moving forward. So z-scores are standard scores. Standard scores, we've got a standard shape. We can find the area under the curve for the z-score. We can start to say if this mean of 31.38, or sample mean of 31.38, has a z-score of 1.8, then we might think that it's a certain distance away from what the mean is supposed to be, and that distance is 1.8 standard units. 1.8 standard units is a bit of a stretch from what we consider normal. When we think back to the empirical rule, given a normal distribution, we know that 95% of all things in your population in a normal distribution fall between 2 standard deviations below and 2 standard deviations above your mean. That's a z-score of -2 to +2. What we have right here is a z-score of 1.8. That's pretty far away from the mean as far as I'm concerned. How far? This far. We go to our table. We look up a z value of 1.8. We find the area between the mean and a z of 1.8 to be 0.4641, meaning the probability of observing a z-score greater than 1.8 is about 3.6%. In other words, the probability of getting a sample of 16 bottles and having the mean of those 16 bottles be 31.38, the probability of that occurrence happening such that the mean of those 16 is greater than 31.38 only happens 4% of the time. Rarely happens. It's not a likely occurrence that we should find 16 bottles whose mean is this far above what the mean is supposed to be. Following through the steps, we looked up that z-score of 1.8. We found the area to be 0.4641. If you need that stuff filled in, when we answer the question here, so what do we conclude? Well, we conclude that it is unlikely. There's less than 4% chance that we could select a sample of 16 observations from a normal population with a mean of 31.2 and a standard deviation of 0.4 and find that the sample mean of those 16 things is greater than or equal to 31.38 ounces. So we get to go to that soda factory and say, hey, you're putting too much product in your bottle, or we just keep our mouths shut and we're happy that we're not thirsty. I want to ask and answer the question, why do we need standard error? Perhaps we're able to see it from this first example. But just like the standard deviation does for a distribution of individual scores, the standard error, as I've been saying, the standard error tells us how much the sample means of a particular sample size vary with respect to one another. When we looked at this problem, we said we have sample size 16 and we know how much means of sample size 16 should vary. That's our standard error. This is a consequence of the central limit theorem. It's that the sample means calculated from a population tend to be closer together than the individual scores from that population. Got a population, take a mean, it's going to be closer to the middle. You're not going to have anything that goes further out than the boundaries of that population. If instead of taking a sample of 16, that QA tech had said, you know what, I'm going to take one, and I'm just going to look at one bottle. We could say that the probability of a single bottle being drawn with 31.38 ounces in it is much more probable than, say, taking 16 bottles and finding a mean that's much higher. And we can do that statistically right here. If we had taken one bottle, we would say that raw score of 31.38 has a z-score of 0.45 because we're only using the population standard deviation. We're not including the fact that it's a sample. We're not worried about any of that. And we can use this procedure because we were told the parent population was normal. If we calculate the z-score here of 0.45, the area between 31.38, aka z-score 0.45, this area is 0.1736. We're no longer talking about the mean of 16 bottles. We're talking about the amount in a single bottle. Over here, this tail is no longer about 4%. This tail is more like 33%. Thus, finding a single bottle, one bottle, from the population that differs by 0.18 ounces is a lot more common than trying to find 16 bottles whose sample mean differs from the population by 0.18. That means you'd have to find, in order to get that 16 bottles, probably 16 bottles, all of which were overfilled, all of which were over 31.2 ounces. Some of them have to be greater than 31.38. Some of them has to be less than 31.8, but they all are probably going to be greater than 31.2. To find a bunch of bottles that gets overfilled, that's less likely than finding one that got overfilled. Before we close with our things to know, I want to take you through one quick little demo that shows you exactly how sample sizes really affect the dispersion here. I'm going to flip over here, check it out. So I've got Excel open here. What I've got plotted here is just a normal curve, and it's a distribution of things. Let's say the intelligent quotient, IQ, which is known in the population to have a mean of 100 and a standard deviation of 15. If we were to say, let's start with a sample size of just 1. We're going to start with a sample size of 1. We could use our z-score formula, and say that if we only look at one person, we're going to randomly select one person. I'm going to use a little estimation here because I want to go back to the empirical rule. We're working normal, so I can do that. We could say that there's 95% of the people in the population fall between 70 and 130, because we're talking about an individual. We're talking about one person. And we've got a normal distribution of the population, and that's what we're talking about. But let's say, as opposed to trying to find one person, we look at two people. We find a pair of people, a couple, if you will. And we took the average IQ of that couple. Now that we're working with a pair of people, we take our standard deviation of 15 and we divide it by the square root of the sample size. That's our standard error. Our standard error here would be, well, it looks like 7.5, because that's what happens when I move up one standard deviation. This is examining pairs of people. We might say 95% of all pairs fall between 85 and 115, where we said 95% of all single people fall between 70 and 130. We're shrinking the boundaries. We're making our distribution more narrow. We know if we're talking about pairs of people, we no longer expect that the two standard deviations in either direction is going to get us to 70 and 130, because individuals vary more than groups do. Well, let's go to a triad here. Now we've increased our sample size to 3. Looks like we've reduced our standard error to 5. Started at a standard deviation of 15, then it became 7.5, now it's about 5. And we can say if we look at groups of 3 people, 95% of groups of 3 people fall between 90 and 110. What if we look at, let's say, a curling rink, which has 4 people on it? We would have 95% of those groups of 4 people should fall between 92.5 and 107.5. We've started sampling groups of people from starting with individuals. We've gone from 1 to 2 to 3 to 4, and our distribution keeps shrinking. Let's add another person. 5 people on the basketball floor. We go from 94 to 106. 9 people on a baseball diamond. 96.7 up to 103.3. We've gone from a single person, and that distribution is pretty wide, where our expectation 95% of all individuals fall between 70 and 130. Now we take all the people who are out on the baseball diamond. We take the average of those 9 people. 95% confident that their average is between 96.7 and 103.3. As we take larger groups of people, our expectations change. Our expectations become more narrow. Our expectations become more central. Let's continue. 11 people on a soccer field. 20 people on an NHL roster, on the bench and on the ice. 53 people on a football team. Now, we're starting with the mean of 100, but with a sample size of 53, we barely go 1 IQ point in either direction. Groups of 53 people don't vary a whole lot. 120 students in my classes. Yeah, we're not even varying hardly any. Let's say we've got 435 members of the House of Representatives. Maybe I challenge what the mean is, but the standard error still allows us to talk about the distribution having a dispersion that is quite narrow. Large sample sizes narrow down your estimates of what the population mean would be. That's not where we get to until we get to chapter 9. So for now, we can review the things that we needed to know out of chapter 8. First of all, the standard error of the mean and how important it is and how to calculate it. Standard error is sigma over the square root of n. We know what sampling error is. Sampling error is the difference between your sample statistic and your population proportion. In other words, x bar minus mu. We've looked at the central limit theorem and what it does. It allows us to say that sampling distributions of sample means are normal if you take lots and lots of samples of the same sample size from any population. Also, it tells us what to do if we have non-normal populations and what sample size we need to create sampling distributions that are normal. We've looked at how the shape of the population affects what our sampling distribution of sample means looks like. We've also just taken a little brief look at how the different sizes of samples might narrow down our estimates of population parameters. And lastly, we did take a quick look at the z-score formula and the fact that the z-score formula is nothing more than sampling error over standard error. Nothing more. I think it's nothing less than sampling error over standard error. That's what I want you to know out of chapter 8. I hope you've learned something, and I hope you come back next time. Until then, stay thirsty, my friends.